Hello there, welcome to this video where we're going to take a look at a mathematics problem that I've selected from an Advanced Extension Award in Mathematics paper. So we're going back here to 2005. I'd almost forgotten about the Advanced Extension Award papers because for the simple reason that not many people actually come to me for help with them. It doesn't seem to be a very popular exam for people to take. People prefer to take the step exams, for example, rather than the Advanced Extension Award. So Advanced Extension Award, actually I had to look up whether it still existed, and as it's quite difficult to find out information about it, but I don't know if there's if it's due to be an Advanced Extension Award in Mathematics exam for 2025. It looks like there was one in 2023, but that's the last paper that I've been able to get any information on. So I've no idea actually if it still exists. If you could give me an update on this, I'd be really grateful. Very difficult to find out information about it. Nevertheless, the problems on the Advanced Extension Award papers they're still useful, they're still interesting, and they're definitely worth looking at if you are preparing for example, a step paper, although the questions on the Advanced Extension Award do tend to be a bit easier, in my opinion, than what you would encounter on a step paper. Nevertheless, there's still some good stuff in there, some good stuff for you to think about, to get your teeth into. Well worth looking at. 2005, just so that you know, this was the Advanced Extension Award in Mathematics paper that I sat. And I remember the problem that I'm going to be going through in this video was the last problem that I managed to complete just before the end of the exam. So I remember the final few minutes coming up to the end of the exam. This was the problem that I was working on. I did manage to answer all of the questions, solve all of the problems. I got a distinction, so I did all right on the exam. And it was interesting to go back to this and actually see if I was still able to solve the problems that 20 years ago I was able to solve. It turns out, fortunately, I am still able to solve them. So I've not gone backwards, thankfully. Okay, so as with my other videos, the whole point of this video really is to capture the problem-solving process. It's not to give you a model solution to a particular mathematics problem. Okay, the specific problem and its solution really is just being used as a way of demonstrating the problem-solving process, how it might occur, what it might look like. For example, so the solution that I give to this problem is my solution. It's not a solution that I've taken from a mark scheme. It's my solution that I've come up with, and I've had to go through the problem-solving process. I've had to make certain observations, develop certain ideas, and it's that kind of stuff that I want to demonstrate to you in these videos. Because what I don't want to do is to give you the impression that problem solving is nice and easy and straightforward, and that solutions to problems just come about like that. And unfortunately, what I find is that the way that mathematics is presented at GCSE and A-level in textbooks and in the classroom, it can often lead people to believe that the problem-solving process is easy and straightforward, or it's non-existent, which is just not the case at all. So what I'm trying to do is to give some motivation about why I'm doing certain things, rather than just going ahead and doing them and saying, yeah, you can do this, you can do that, and you get the solution. Actually explaining, trying to describe to a certain extent what it was that motivated me to do this or that or the other. Okay, so just before we start, I'd be really grateful, by the way, guys, if you wouldn't mind hitting the subscribe button for this channel and hopefully giving this video a like. I'm trying to reach out to a wider audience because I'm really wanting to help people who are preparing for step exams, preparing for mathematics admissions tests. I don't make anything from making these videos. You probably guessed that from the production quality of these videos, or lack thereof. I don't make a penny from making these videos. I make these videos for the hell of it. I make them because I want to make them and because I want to help you. So it'd be really great if you are benefiting from these videos, if you could show your support just by hitting the subscribe button. It doesn't cost anything. but I'd be really grateful if you could do that. Cheers, guys. Okay, so let's have a look at the problem for this video. So it's question number 4 that we're looking at from the 2005 Advanced Extension Award in Mathematics paper. Let's have a look then. So I've already drawn a diagram up here just in preparation. The information that we're given is a rectangle ABCD is drawn so that A and B lie on the x-axis, C and D lie on the curve with equation y equals cos x, such that minus pi by 2 is less than x is less than pi by 2. The point A has coordinate p0, where 0 is less than p is less than pi by 2. Okay, so if you're not in the habit of drawing diagrams, get into that habit, okay? Diagrams are very useful. I'm not saying that diagrams will always be exactly what you need to do, but they're going to be very useful to you in a great number of circumstances. When it comes to solving a number of problems, diagrams are going to be really indispensable to you. And it's amazing to me that at GCSE and even at A level, there's still so many students that will refuse to draw diagrams unless they're specifically told to do so, because in their minds, if they're not told to do something, they understand it as it's not worth doing, because they're not going to get marks for doing it because they've not been told to do it. But that's just not true at all, okay? Sometimes you're not told to do a specific thing because there might actually be several possible ways in theory of going about something. It's just that really there's one way which is going to be easiest, and you're expected to notice that, to demonstrate your understanding. Sometimes you've just got to go ahead and you've got to do some things to make your life easier. But what can happen is if you refuse to draw diagrams, or if you refuse to do something because you've not been specifically told to do it, because you think that you're not going to get marks for doing it and therefore it's not worth doing it, you might actually be making a rod for your own back by not being able to actually find a solution to the problem. It might be that by drawing a diagram, you actually reveal clearly what the direction of the solution needs to go in. Okay. Plus, it's a good thing for you to be able to interpret written information diagrammatically and vice versa, right? So if you might need to solve an algebraic problem, but the solution to that algebraic problem may be easier to see in a diagram. Okay, so you're getting the best of both worlds. You can use algebra to tell you about what's going on in the diagram, and you can use the diagram to tell you what you might need to do with the algebra. Okay, so it's definitely worth doing. So I've added a little bit extra information onto this diagram. So I've put the coordinates of B, C, and D in here because we know that ABCD is a rectangle and not just a quadrilateral. I know that CD must be parallel to AB, and therefore C and D must be at the same height, so to speak, above A and B respectively. And because of the symmetry of the graph of cos, then C and D must also be, the rectangle must be symmetrical about the y-axis. I guess that's the top and bottom of it. So that justifies these coordinates here. And also I've used the fact that cos is an even function. Rather than writing cos minus p in here, I've just written cos p. Okay, it's probably not actually going to make any difference. From what I can remember, it doesn't really make any difference, but I've just included that bit of information anyway. So the first bit that we're given, or the first question, is find an expression in terms of p for the area of this rectangle. So this is dead easy. If you know how to find the area of a rectangle, then this should be very straightforward. If you don't know how to find the area of a rectangle at this stage, then, well, that's your problem. So the width of this rectangle is 2p. By symmetry, so that distance is p. By symmetry, that distance is p, so the whole distance is 2p. The height is cos p. And that's it, right? 2 marks. 2 marks for that throwing marks away. Now, one difference that you might see between kind of normal A-level maths exams and Advanced Extension Award or STEP exams is that there's much more responsibility on you personally to derive the results that you need that are going to be used in subsequent parts to the problem. So here, for example, in part A, find an expression in terms of P for the area of this rectangle. If this were a normal A-level maths exam, or if it was in one of the kind of more modern textbooks for the A-level maths course, what I'd expect the question to be wiping your backside a little bit more for you, in the sense that I would expect them to say something like, show that the area of the rectangle is given by the expression 2p cos p. Okay, so that even if you fail to show that in a suitable way, you can still use that result to access the marks in subsequent parts to this problem, if it's a more structured problem, if it's a multiple part problem. Whereas on STEP and Advanced Extension, you've got to figure it out. And if you don't figure it out, well, tough. You don't get those marks, and you don't get the marks for the later parts of the problem. And that's your lookout. Does that sound cruel? Does that sound mean? Okay, maybe, but that's how it is, okay? So that's one difference that you might notice between the style of problems that you're given on normal maths exams in textbooks and on more challenging exams such as STEP or Advanced Extension. Okay, so that was easy. So we'll call that A, by the way. A equals 2p cos p. And then part B, the maximum area of ABCD is equal to S, okay? And this occurs when P is equal to alpha. We need to show that pi by 4 is less than alpha is less than 1. Okay, pi by 4, less than alpha, less than 1. So, be prepared to think quite carefully. Be prepared to use everything that you've been taught, is what I can say. I mean, obviously, you can't necessarily know absolutely everything, but be prepared to use as much as you know, because it could crop up at any point. Now, because we're talking about the maximum area of ABCD, I think it's quite natural here for us to think in terms of differentiation, because we're talking about the maximum of a function, effectively. That's not to suggest that the maximum value of a function is always identified through differentiation, finding turning points and things like that, but it's a very common thing, right? Particularly at A level, hopefully at this point you've been almost conditioned, really, to think differentiation when you're talking about maximum and minimum values of functions. This is not necessarily a bad thing, but just understands that sometimes in some sets of circumstances, the maximum value of a function is not necessarily at a turning point. And it really does depend to a certain extent on the domain of the function and things like this. But that's not something that we need to consider too much here. It is differentiation that we're going to need to do. Okay, so let's differentiate A with respect to P. Now, this is a product of functions. Do I need to remind you to use product rule? Hopefully not. Okay, hopefully you recognize that when you've got a product of functions and you need to differentiate it, you need to use product rule. Okay, unless there's some way that you can write that function, rewrite it so that it's not a product of functions anymore, then you're going to need to use product rule. Because it's bewildering to me that people still are coming up to their final exams at A level and they still fail to use product rule when they're trying to differentiate a product of functions, or fail to use chain rule or something like that. So I might give them, let's say I give somebody x cos x, or let's make it a little bit different, x squared cos x. I might give somebody this to differentiate. And they'll come back to me and they'll say, okay, so dy by dx equals 2x minus 2x sine x. And I'll say, how have you done that? And they'll say, oh, when you differentiate x squared, you get 2x. And when you differentiate cos x, you get minus sine x. So when you multiply these two together, you get minus 2x sine x. So they've basically made their own product rule, which doesn't work. Okay? And you can do that. You can invent some sort of operation, I guess, that differentiates in this way. But it's, as far as I know, it doesn't really correspond to anything of use. And it's definitely not how we would typically differentiate a product. So this is not correct. So big exclamation marks around that. This is not correct. Please use product rule when you need to use it. And yes, you will have to decide when you need to use the product rule. So one thing that I know that people have difficulty with is actually making the decision for themselves when to use certain techniques. And this is what's one of the things that's really going to distinguish those people that get higher grades from those people that get lower grades. The people that get the lower grades, often one of the problems that they have is that they're waiting to be told exactly what to do all the time. They don't understand the techniques well enough, or they're not confident enough with them to actually make the decision for themselves in various situations about which techniques to use. You have to make that decision, especially on one of these more challenging exam papers. So what do we get when we differentiate this? I'm not going to go through all of the details, but we get 2 cos p minus 2p sine p. Okay, 2 cos p minus 2p sine p. Okay, so what it might be worth noticing at this stage is that dA by dP is a function in its own right, but it's also a continuous function. Okay, now you don't need to know at A level, you don't need to know a precise definition of continuity of a function. Okay, that's something that will come if you go into university to do undergraduate maths. You will learn that. You will learn several definitions of continuity. There's not just one type of continuity, but you'll learn all about continuity and stuff like that. At this stage, we take continuity as meaning simply a continuity of a function, meaning that we can draw the graph of the function without taking our pen off the paper, in theory, right? Not a satisfactory definition once it gets onto higher level maths, but it suffices for what we need at this stage. Maybe back in the 1700s or something, that would have been a satisfactory definition of a continuous function. But now, in contemporary modern mathematics, no, something much stricter needs to be used. But nevertheless, we understand that this is a continuous function. Okay, and it may be. Is it worth you pointing this out? Yeah. Okay. Do you have to point this out? I don't know. It depends on the mark scheme, right? And whether you get your marks. But my advice to you is, any observations that you make, just make a note of it. Because if you don't make a note of it, then basically you haven't made, as far as your examiner is concerned, you haven't made that observation. And it might be something that's actually really important. Okay? So for the time that it takes, for the effort that's involved in actually just noting and writing that this function is continuous, just do it. If you notice that. If you don't notice it, okay, you don't notice it, that's a separate issue. But if you do notice it, just make a note of it. Because actually, what we're going to be doing in a second does rely on the fact that this function is continuous. So it took me a little bit of time to figure out exactly how to do what I'm about to. I knew what I needed to do. It was just actually figuring out exactly how I was going to do it. So when we've got a continuous function, remember that we've got this kind of sign change rule that if so if we've got f of x is a continuous function, f of a is and a is less than b, and f of a is greater than 0, and f of b is less than 0, then there's some c in between a and b such that f of c is equal to 0. Okay. There might be several, by the way, there might be several possible values of c between a and b. There's nothing suggesting that there's just one. If we think about this in terms of a diagram, we've got our x-axis here, which is extends indefinitely in either direction. F of a is up here, f of b is down here. We've got to somehow get from here to here. Well, that means that we must pass through the x-axis at some point. We might go through several times. We might do something like this. Okay, but it's going to be at least once that we pass through, and that's the kind of idea that we're going to be using here. And this is only valid with continuous functions. If we've got discontinuous functions, which occasionally do come up, depending on which exams you do, discontinuous functions may occasionally appear, but they will be obviously discontinuous because they'll be like things like step functions, for example. They'll have huge breaks in them. It does turn out that there are discontinuous functions that are very, it's not necessarily easy to determine that they are actually discontinuous. You'll learn all that kind of stuff when you go on to undergraduate maths. Look forward to it. It's fun. It's interesting. Okay, so let's say when p is equal to pi by 4, what do we get? We get dA by dP is equal to 2 cos pi by 4 minus 2 pi by 4 sine pi by 4. We don't have a calculator in the Advanced Extension Award exam. You shouldn't need a calculator to figure out what cos pi by 4 and sine pi by 4 is. If you don't know those, get it sorted. So cos pi by 4, root 2 over 2. So 2 cos pi by 4 is just going to be root 2. 2 pi by 4 times sine pi by 4 is going to be just root 2 times pi by 4. So take root 2 over 4 out as a common factor. We get 4 minus pi. And that's going to be greater than 0. Why? Since 4 is greater than pi. Right? Since 4 is greater than pi, 4 minus pi is going to be greater than 0. So positive times positive is going to be positive. Do make a note of things like this. Don't just say this is greater than 0. Justify it. Justify everything. Okay? So now we've got, what about with p equals 1? Well, p equals 1, we get dA by dP is equal to 2 cos 1 minus 2. 2 times 1 times sine 1. Okay. So remember, we don't have a calculator, and I don't know what the value of cos 1 is. I don't know what the value of sine 1 is. We're not in the business of using approximations. We need to use, if we're going to use any values, we need to use exact values, or we're going to have to go via some other method. Okay. Don't notice here for pi, I've not even said, well, pi is kind of 3.14. All I've said is that pi is less than 4. Okay. So when you're doing pure maths, you do need to work with exact values. As soon as you start working with decimal approximations, really, you've gone beyond doing pure maths. Okay, so again, this is still something that some A-level students are in the habit of doing, using decimal approximations. Okay, when they can't be asked to work with exact values, when they struggle to work with surd expressions and e to the power of 2 and things like this, and they'll still reach for the calculator and replace it with a decimal approximation in some cases. This defeats the whole object of things like integration. When you're doing integration, if you're just going to approximate everything, you might as well just replace integration with basically trapezium rule or something like this, or Simpson's rule, and just approximate areas. That's not the point, right? Integration is a precise thing. It gives you exact areas. Okay, so we've got to figure out a way to deal with this, and it did take me a little bit of time just to figure out what to do, but it comes down to using this again. Okay, so if 4 is greater than pi, then 1 is greater than pi by 4, or pi by 4 is less than 1. So let's have a look at the graphs of sine x and cos x, kind of superimposed. So that's cos x, that's sine x. So y equals cos x, y equals sine x. We've got a point of intersection here at pi by 4, where they've both got the value root 2 over 2. And then we've got 1, which is somewhere between pi by 4 and pi by 2. Okay? Well, what can I see then here? I can see that at x equals 1, cos x is going to be less than sine x. And therefore, cos x minus sine x is going to be less than 0. Right? Or maybe I should have replaced these with 1. So cos 1 is less than sine 1, cos 1 minus sine 1 less than 0. Okay, so if cos 1 minus sine 1 is less than 0, that means that 2 cos 1 minus 2 sine 1 is going to be less than 0. Okay, and do make a note of these things again. You've got to justify what you say. So although you might have a clear idea in mind that you want to use this sign change rule and that you've shown that this is greater than 0, and then you've got here, don't just write, oh, this must be less than 0. No, you've got to show how it's less than 0. Okay, you've got to show in a convincing way. It's very important that you do that. Do not think that your examiner is stupid. Do not think that you're going to be able to outsmart your examiner. You may be very good at mathematics. You may be very talented at mathematics, but at the stage that you're at now, you are not better than your examiner. Your examiner knows way more about mathematics than you do. That will change for some of you. That will change over the coming years. Some of you will become top mathematicians, and you go into research, and you may go on to do some great things in mathematics. But at the stage that you're at right now, your examiner knows way more about mathematics than you do. You're not going to be able to fool them. You're not going to be able to pull the wool over their eyes. Don't even bother trying. Okay, so I'm not going to write it out exactly what my conclusion is going to be, but you do in an exam. All I'm going to do is I'm just going to tell you what my idea is. So when p equals pi by 4, dA by dp is greater than 0. When p equals 1, dA by dp is less than 0, and therefore, since dA by dp is a continuous function, there must be a value alpha which is greater than pi by 4 and less than 1, such that dA by dp is equal to 0 when p is equal to alpha. Okay? And it's as simple as that. So it's just as simple as using the sign change rule. So that's it. That's the second part done. Now we're on to part C. So I don't think there's anything here. I think I'm going to need this derivative. I don't think I need any of the other stuff. So what I need to show now for part 3 is that s is equal to, let me get this right, 2 alpha squared over square root of 1 plus alpha squared. Is that right? Yeah, 2 alpha squared over square root of 1 plus alpha squared. Okay, so remember what S stands for. S is the maximum value of the area. Okay, and this occurs at alpha, when p equals alpha. So using this formula, we know therefore that S is equal to 2 alpha cos alpha. And what we're going to have to do here really is just kind of just mess around with the algebra until something works. That's all I did. There wasn't a specific thing. Once I saw this, there wasn't one specific thing that I thought, I have to do that. It was just, okay, just play around with the algebra. Eventually something will turn up that's useful. And literally that's how it is in some cases. So what I also know is that when when p equals alpha, we get 2 cos alpha minus 2 alpha sine alpha is equal to 0. So after a bit of messing around, I figured out what to do. Like I said, this didn't happen straight away. It took me a few minutes, probably 5 minutes or so, to figure out what to do. This is normal. Give yourself time to think. Okay? Accept the problem-solving process. Accept that you need thinking time. Don't put so much pressure on yourself as to think that you've got to do everything straight away. Now. Because you don't. Okay? You don't need to do that. So there's all different ways that we can potentially go about this. So I've actually got a way here that I've in my notes that I've done. I'm actually going to try a different way. So we've got, for example, using this, we get cos alpha equals, what is it? S over 2 alpha. Cos alpha equals S over 2 alpha. So, if this is alpha, cos alpha is S, is adjacent over hypotenuse. So if that's the adjacent, that's the hypotenuse. What's the opposite going to be? The opposite's going to be 4 alpha, square root of 4 alpha squared minus s squared. So therefore, coming back to this, what do I get? I get 2 cos alpha, which is s over 2 alpha, minus 2 alpha times sine alpha. Now sine alpha is opposite over hypotenuse, square root of 4 alpha squared minus s squared over 2 alpha, and that's got to be equal to 0. Okay, so cancel. Nice. S over alpha minus the square root of 4 alpha squared minus s squared equals 0. And then it's just going to be a rearrangement of this thing. So could have organized things a little bit better, I guess. But we get s over alpha equals the square root of 4 alpha squared minus s squared. So square both sides, s squared over alpha squared equals 4 alpha squared minus s squared. So s squared equals 4 alpha to the 4th minus alpha squared s squared. So 4 alpha squared is equal to s squared times 1 plus alpha squared, and therefore s squared is equal to 4 alpha squared over 1 plus alpha squared, and the result is going to follow. Square root each side, you get 2 alpha squared over square root of 1 plus alpha squared. Okay, so that wasn't actually the way that I originally did it. So I've got my notes here, and I actually prefer this way. I did it a completely different way, using trigonometric identities, rearranging this, using the identity cos squared alpha plus sine squared alpha is going to be equal to 1. Find an expression for sine squared alpha. I mean, it amounts to more or less the same thing as what I've done here, but I actually just prefer this way, to be honest with you. So that's that done. That did take me a good 5 or 10 minutes to figure out that, but we got there in the end. And then finally, onto the last part. By the way, if there's anything that you don't understand in this video, please leave a comment in the comment section. If there's anything that if you don't understand something, you don't understand it, and it's better for you to get clarification. I really want to help people develop their problem-solving skills. So don't be ashamed about asking a question. Don't be embarrassed about asking a question. Okay, I'm here to help you, and I want to do that. Right, okay, so then we're on to, now, okay, word of warning, be very careful what you do, what conclusions you draw, okay? Like I said earlier, your examiner knows way more about mathematics than you do. If the logic doesn't add up, no pun intended, then your examiner will spot it, okay? And that's particularly pertinent here because it's a very crafty thing that they ask for the final part here. Very, very crafty. And I'll explain why as and when we get there. So what we've already shown, we've shown that pi by 4 is less than alpha is less than 1. And we've shown that s is equal to 2 alpha squared over square root of 1 plus alpha squared. Now we need to show, so this part 4, show that pi squared over 2 root 16 plus pi squared is less than s is less than square root of 2. Okay. So, here's the thing. Here's what I think a lot of people would be tempted to do here, because it will appear to work. And this is why it's so very crafty what they've done. If you plug in, so you've got the expression for s here. If you evaluate this, if you replace alpha here with pi by 4, as if alpha was a variable. Actually, it's not, it's a constant, right? Alpha is a constant here. And understand that alpha is a constant. If you plug in here, replace alpha with the value of pi by 4, what do you get? And you do a bit of rearrangement, you'll get this. Okay? So it would naturally seem to follow that s is going to be greater than the value of this expression with alpha replaced with pi by 4. Because alpha is greater than pi by 4, right? And also alpha is less than 1. Now, when you plug alpha, replace alpha with 1 in here, what do you get? You get square root of 2. So it would naturally stand to reason, right, that since alpha is less than 1, that when you replace alpha with 1 in here, that you get something that is going to be less than s, or something which is going to be greater than s. This is totally wrong. Okay? Unfortunately, it doesn't work. Right? So if you're thinking about this as some sort of function, s of x maybe, then replacing the x with pi by 4, alpha and 1, you don't get that s of pi by 4 is less than s of alpha is less than s of 1. S of alpha is this thing, or just s or whatever. S of pi by 4 would be this expression, s of 1 would be this expression. It doesn't work. Okay, you've got to be much more subtle about it. So yes, we know that pi by 4 is less than s is less than alpha is less than 1. We are going to need to use that. And we are going to need to use the fact that s is equal to, I've forgotten it already, it's 2 alpha squared over square root of 1 plus alpha squared. Okay, so I can say that when I plug, so if we think about this as a function of x, maybe s, or maybe the area of x, or area of p, whatever, a of p equals whatever. I know that the area of this rectangle is going to be less than s at pi by 4. Okay, so if I do replace alpha with pi by 4 for the, I could find an expression for the area in terms of p, and it would come out to be, it resembles this, 2p squared over square root of 1p squared. Okay, so when p equals pi by 4, I do get that the area of pi by 4 is less than area of alpha, which equals s. Okay, when I plug pi by 4 into here, what do I get? I get this thing. I might need to do a bit of tidying up. Let's have a look what that might look like. So I get 2 pi by 4 squared over square root of 1 plus pi by 4 squared. So this is going to be 2 pi squared over 16 all over square root of 1 plus pi squared over 16, which is multiply numerator and denominator by 16. So I get 2 pi squared over 16, square root of 1 plus pi squared over 16. Take the 16 out, 2 pi squared over 4 square root of 16 plus pi squared, and cancel by 2, get pi squared over 2 square root 16 plus pi squared, okay, which is what I need. That's true. Why is that true? Because I'm told that S is the maximum value of the area. So any other area of this rectangle is forced to be less than S. So in particular, when P equals pi by 4, which is not equal to alpha, where the maximum occurs, the area of the rectangle is forced to be less than S. And that's why it doesn't work if I just replace P with 1 in here. Because I'm told that alpha is where the maximum occurs. So even if I plug P equals 1 in here, that means that I'll get an area for the rectangle, but it's actually forced to be less than S, not greater than S. So I've got to figure out a different way, even though when I plug 1 into here and I simplify it, what will I get? I'll get this. I'll get the square root of 2. That's why it appears to work. Only appears though. Doesn't actually work. So I've got to be a bit more subtle about things. So we start with 2 alpha S, which equals 2 alpha squared over square root of 1 alpha squared. Now I'm going to have to look at my notes because I can't remember the exact steps that I took for this. Okay, but it starts with alpha is less than 1, so alpha squared is less than 1. Okay, and therefore alpha squared plus alpha squared, which is 2 alpha squared, is less than alpha squared plus 1. So all I've done here is just added alpha squared to either side of this inequality. Okay, so therefore 1 over 2 alpha squared is going to be greater than 1 over alpha squared plus 1. Remember, when you if x is greater than y, then 1 over x is going to be less than 1 over y. I've got to flip the inequality. So therefore 1 over square root of 2 times alpha is, because these are both positive quantities, is going to be greater than 1 over the square root of alpha squared plus 1. Therefore, multiply each side by 2 alpha squared. Is it 2 alpha squared or just 2 alpha? 2 alpha squared. 2 alpha squared over square root of 2 alpha is forced to be greater than 2 alpha squared over square root of alpha squared plus 1. Okay, notice that this means that 2 alpha square root of 2 times alpha is greater than S. Now that's not quite what I need, right? I need square root of 2 is greater than S. But alpha is less than 1. So square root of 2 alpha is less than square root of 2. So if S is less than the square root of 2 alpha, S is also less than the square root of 2. Which gives me my other inequality here. This might seem a bit fussy. And you might think, do I really have to go through that to show this? Well, maybe there's another way that you can do it, but yeah. You can't half-ass things. Or if you do, then you're going to risk losing a significant number of marks on an exam. Okay, so it's just not worth it. It's not worth the risk, in my opinion. You've got to do what you've got to do, and it took me a good few minutes again, probably 10 minutes or so. This was, in my opinion, this is possibly one of the hardest, most difficult problems on this paper. I've done a couple of the other problems and I kind of flew straight through them. They weren't really too difficult. Even thinking back to when I was doing my A-level maths, just around the time I was sitting this exam, I can't imagine that I would have had difficulty with too much difficulty with certain other questions on this paper. Kind of flew through them. This one, on the other hand, was, in my opinion, probably why it was the last question that I attempted when I did this paper. It was one of the more difficult ones, if not the most difficult on the paper. And you have got to give yourself time to think, but the logic has to stack up. The logic has to point towards what it is that you're trying to show. If it doesn't, your examiner will pick up on it and you will be penalised for it. So don't try to pull the wool over the eyes of your examiner. You're not going to be able to do it. So, okay. This comes about then through the fact that S was we're told that S is the maximum value of the area. So therefore, this is the area of the rectangle at pi by 4, which is forced to be less than S. And then we deduce this other inequality from the fact that alpha is less than 1, but not simply by subbing 1 into our formula for the area of our rectangle. Okay, so that brings us to the end of this problem. I know it's been a bit rambly in some parts, but that's the whole point of these videos, to be honest with you, that I'm presenting the problem solving process. I'm not just giving you a model solution. I'm actually allowing my thoughts, my spontaneous thoughts to be captured, because they are part of the problem solving process. And you have to learn to deal with these sometimes quite intrusive thoughts from time to time. So you'll have an idea and you'll be getting distracted with other things, and you've really got to learn to think clearly and stay focused and things like that, while at the same time acknowledging that you are potentially having other ideas. So if there is anything that you're not clear about, feel free to ask in the comments section. I'd be happy to help you. If you are looking to do a step paper, prepare for a step paper, mathematics admissions test or whatever, and you would like some help with your preparation with that, feel free to get in touch. I'd love to have a discussion with you about what your needs and requirements are and what you're aiming to achieve and how I can help you. So please feel free to get in touch. So that brings us to the end of this problem, and it brings us to the end of this video. Thanks a lot for watching.